Whoa,
Okay, just a couple of things here. Maybe more people will show up here in a second, but let me go, where am I? Oh. Okay, we got one more. Okay, just a quick share here of the course website, just to kind of give you an update, just to remember what's coming up. This next week, we have exam number 2. As the last one, it will open up on a Friday, the 2nd, at 7 a.m., and then close that Saturday at 11:59. So give yourself plenty of time. Also, it will require what is called the lockdown browser. So what I've done, if you haven't done it yet, I put up a extra credit, and just a couple of questions, nothing complicated. One is a very general chemistry question. The other one is basically asking you, is the lockdown browser working for you? Just type in yes, and if it's not, type in what's the problem, and we'll see if we can figure it out. And then that thing is worth 10 points, okay? So it's just a test. We got homework on the 28th for chapter 5, the 1st through chapter 6, and then, of course, you have the next online lab number 5, which is due on Friday. So any questions about that, just to kind of give you a heads up. Then the following Friday, there'll be a midterm kind of lab exam. And that normally we call that, they had a different name, but since we're doing online, and basically I'm taking questions from labs 1 through 5, creating a little small exam, and that'll be your midterm for the lab, and that'll be next Friday. On the 9th, not the next Friday, but the 9th, following Friday. All right. Any questions? No?
no thank
All right. All right. Sounds good. Welcome aboard, Mitchell. Well, let me proceed with where we ended, which is this particular slide. And we were talking about what's called the electron configuration. Now, what this does is a notation that allows us to write how the electrons are situated around the orbit of the atom. And it's a very specific notation that we utilize. It gives us a lot of information with respect to explaining why certain elements want to lose electrons and certain elements want to gain electrons. The ultimate goal for all of them is that they want to obtain on the valence shell, the outermost shell, the octet or the 8. They want to follow the octet rule. They want to maintain 8 electrons around the outermost shell. Now that happens for metals, for example, by losing electrons. Those orbits that those electrons of valence shell were on are no longer there, so that now the valence shell is the next orbit in, which is full. So that's the driving force for metals and why they all want to lose electrons. With respect to nonmetals, they want to gain electrons. So nonmetals want to gain electrons, and by doing that, they fill up the outermost shell to obtain the octet rule again. So in both cases, losing or gaining electrons, they want to have the same number of electrons as the noble gas either in front of them, if they're nonmetals, or they want to have the same number of electrons of the noble gas behind them if they are nonmetals. Excuse me, if they're metals. Okay, they want to be what's called isoelectronic. Same number of electrons. Now, the key point here is they're not becoming the noble gas. To do that, obviously, as you well know, hopefully, is that to become a noble gas, they got to lose protons because the protons define what an element is. Well, we're not losing protons here. We're either gaining or losing electrons, which we can do all day long, or neutrons. We can lose all those, but we never change what the element is. Okay, so, and then by doing that, it creates what are called ions. So we get the element, which is neutral because they have an equal number of protons and an equal number of electrons. And once they gain or lose an electron, now they become what are called ions. They are ionic in nature. They have a full charge, either full positive or full negative charge. Now, there is a change in as far as the charge itself. There's a magnitude to that charge, and that's dependent on how many electrons are lost or gained. If you lose one electron, you have a +1 charge. If you lose two, you got a +2. And obviously, if you lose three, you get a +3 charge. The converse of that is if you gain 3, you got a -3, or gain 2, -2, or gain 1, -1 charge, okay? Because now, another way to look at it is if you count the protons and the number of electrons, when they're elements, there's neutral. There's no charge at all. But if you gain electrons, you got now a net negative charge because you got more electrons. And if you lose electrons, you got a net positive charge because you lose some electrons which have a negative charge. Okay. All right. So the electron configuration for sodium, for example, is given as 1s2, 2s2, 2p6, 3s1. Now, the number in front, to refresh your memory, the coefficient, is the energy level. So in the first energy level, which corresponds to the period that they're in, so period 1, that's the first energy level. And recall that in the first period, there's only one sub-energy level, or what we call orbits. There's 4 orbits. There's the S, the P, the D, and the F. Okay, in the first energy level, which is the first period, there's only the S orbit, one S orbit, and every orbit can handle the maximum of 2 electrons. So the first energy level, 1s superscript 2, denotes that there are 2 electrons in the first energy sub S orbit. Okay, now the second energy level, which corresponds to the second period in the periodic table, has 2 types of orbitals. They also have the S, but they also have the P. Now in the P, there are 3 P orbits, and each one can handle a maximum of 2 electrons. So all the P's have a maximum electrons of 6, and the S's have a maximum number of electrons of 2. So in this case, 2 orbits in the second period, we have the S and the P. So it's 2s2, 2p6. At this point, you are at 10 electrons, which corresponds to neon. Now, sodium is in the third energy level, third period, and it's in that first column. I'll bring a periodic table here in a second, so we can use the periodic table to very quickly write down the electron configuration. Or you can memorize the way that we fill in the orbits. But I prefer to use a periodic table because it's very quick. So the last electron for sodium is in the third energy level and S1. Okay? S1. And so that is the electron configuration of sodium. If you count all the superscripts, you will see there's 11. Now, the outermost shell, the valence shell, is in the third energy level. And that's highlighted here as number 3. So that corresponds with sodium being in the group 1A. Sodium has 1 valence electron. That 1 valence electron occupies the third energy level of the S orbit. The S orbit in the third energy level. Okay. Now, they have the capability. sodium has a capability to gain electrons, but it's got to gain 7 of them to maintain that 8, to get that octet. And so from an energy perspective, it's much easier to lose 1 electron and get rid of that 3s1, okay? And when it does that, it ends up with a positive charge, okay? And becomes an ion. And so now the valence shell for the sodium ion is now in the 2nd energy level, and that is full. It has 10 electrons now, which is the same number of electrons as the noble gas behind it, which happens to be neon. So sodium ion is isoelectronic with neon, okay? It is not neon, but is isoelectronic as neon. So the driving force here is to get to that octet. In the case for metals, by losing electrons, it gets rid of the electrons in the outermost shell, and the next one is full. And now it has the magical 8, or the octet. Now, let's take a look at sulfur, okay? Sulfur has 16 protons and 16 electrons. So if you look at the electron configuration, it is just like sodium, 1s2, 2s2, 2p6, and it's in the 3rd energy level, so we go up to 3s2, and if we shoot across on the periodic table, we find that sulfur is in the 4th column on the far right side. So that tells you that there are 4 electrons, okay? And so the electron configuration for sulfur in the neutral state, the element, is given as follows. Now look at the valence shell. It's in the 3rd energy level. Now think about it from an energy perspective. You know, is it easier to get rid of 6 electrons or just dump in 2 more? And it really is easier to dump in 2 more, because first point is it's a nonmetal, and nonmetals want to gain electrons. And here sulfur has the capability of gaining 2 electrons because it has 2 vacancies in the 3p orbital, okay, because I can get a maximum of 6 there. And so by gaining electrons, now the valence shell is full with 8, the magic 8. In the meantime, its new charge now, the ionic charge, is a -2 because it gained 2 electrons. And that configuration for the ion is isoelectronic with argon, okay? Argon has 18 electrons. And so again, the nonmetal's driving force by gaining electrons is to be isoelectronic with the noble gas in front of it. And metals, specifically the groups 1 and 2, is to be isoelectronic with the noble gas behind it. The other metals are the inner transition metals, the B elements. We cannot predict like we can with the 1A and the 2A because they can have variable oxidation numbers or charges. For example, copper can have a +1 or a +2, depends on the reaction conditions. But more said on that later down the road. Okay, and so let me pull up the periodic table, and I believe I sent this out to you. Okay, and what I did with this periodic table, our standard periodic table, I numbered on the left side the periods or the energy levels. There are 7 energy levels at the present time. We have 118 elements. By the way, right now I read that they're working on trying to get to 119, which is predicted to be in period 8. Let's see how we might hear more about that in the next few months. All right, so for groups 1A and 2A, I think of those as what we call the S elements or the S block, okay? Notice that there are 2 columns in the S block, the first column and the second column, which is consistent with the S orbits that can handle 2 electrons maximum. okay? If we shoot across to the 3A that's underneath boron and we go all the way across, think of those starting at 3A as the P elements or the P block. There are 6 columns in that P block, okay, starting with boron. If we go from boron, number 5, shoot across the periodic table, we got 6 columns, which corresponds to P1, P2, P3, P4, P5, and P6 as we go across the periodic table. Now, for the B elements, the ones labeled, 3B, 4B, and so forth, think of those as the D block or the D elements, okay? And if you count from number 21, scandium, go across to number 30 to zinc, guess what? There are 10 columns there. The D orbitals have 5 D orbits. Each one can handle 2 electrons, total of 10. So if we start to fill up the D, we start with number 21, and you won't fill up the D's until you hit element 21. From elements 1 to 20, there's no D electrons to worry about. But the moment you hit 21, now you got to deal with the D elements and shoot across the periodic table to D10. Now here's the part that can be a little bit confusing. If we look at element 21, okay, it is in the 4th energy level, 4th period, okay? But the D orbits, because of the mathematics of these orbits, which are mathematical equations, do not come out in the 4th energy level. They actually come out, they exist in the energy level before that. So in this case, the D's for 21 will start off with 3D1 for 21. Okay, 3D1. And so for the D, for starting at 21, when the D orbits kick in, they're not in the 4th energy level, they're actually in the 3rd energy level. If we look at number 39, also a D block element, also in the 5th period, not also, but in the 5th period, but its D electrons or D orbits come in the 4th. So basically, when you hit the D block, you look at the period it's in and just subtract 1, okay? So for 21, it would be 3D1. And if we went across, all the way across the zinc, guess what that would be? 3D10, okay? All right. For the F block, starting here with 59, notice that they are in the 6th energy level, but the F orbits actually go in 2 energy levels. And so if we were to do a 59 element, the F block would actually be 4F1. There's 10 columns as you go across these elements in period 6 and 7, the ones that are pulled out of the periodic table. Okay, and that's the only part that can be a little bit confusing, the D and the F. So subtract 1 for the D from the period it's in. For the F, subtract 2 from the period that it's in. Okay. All right. So we can very quickly, let's do using the periodic table, the electron configuration for chlorine. Okay. Well, first thing I do, I find chlorine. It is in the 3rd energy level. Okay. So that means that we're going across the periodic table from left to right. The 3s2 is full. And then the second thing is it's in the 5th block of the P, it's in the 5th column, I should say, of the P block. So that tells you P5, okay? P5. And so if we were to start the periodic table, the electron configuration, obviously the 1s2 is full, okay? So that takes care of all of the electrons up to helium, okay? And then the second energy level is full. So the 2s2, as we go across from lithium to beryllium, those are filled up with the electrons. That's the order that we fill them up. And then we shoot across all the way across the neon. And that is 2p6. Neon's in the 6th column of the P block. Okay? So at this point, with respect to electrons, we're already at the neon number at 10 electrons. If you count the subscripts, you'll see you got 10, 6, 2, and 2. That's 10 electrons. We go around the horn. We go to the third period where sodium's at begins, and we're going across the periodic table. Well, being in the third energy level going across, we see that the S orbit is full. And now we come across to the 3A to the T block, and that we're still in the third energy level in the P block now. And we see that chlorine is in the 5th column, so that would be 3p5 in the 5th column of the P block. And so that is the electron configuration of chlorine. And if we kept shooting across to argon, we just changed that 5 to 6. Okay? And if we wanted potassium, which is number 19, okay, so we go around the horn, we're in the 4th pair, potassium is 4s1. And so sequentially, that's all you got to do. Just keep going. Okay, and that's potassium, and that's potassium number 19. Oh, excuse me, sodium. Where am I? Yeah, potassium. I'm sorry, my eyes got lost here. So potassium is number 19. If we go to calcium, is right next door to potassium, and we change that 1 to a 2. Okay, so now we are at calcium. That is the electron configuration for calcium. And if we wanted for some reason to go into number 21, you see that it's in the D block. So that means the D orbits are beginning. Okay, and keep it in mind that the D orbits are 1 is the period it's in minus 1. So the D block starts off at 3, and then D, and it's the first column, and that is number 21. Okay, and if we wanted to do zinc, which is number 30, we just continue across the columns. There's 10 columns, and that would be zinc. And from 31, which is the next one of zinc, we're back in the P block, which puts us back in the 4p1. Okay. So that would be the electron configuration for number 31. So sequentially, all we did was just keep adding the electrons in the different energy levels of whatever position the element is in. Okay, so you can use the periodic table very quickly to figure out the electron configuration. Now, there is a shorthand way to do the electron configuration, and you're more than welcome to use this shorthand way. If the question asked doesn't state, do not use shorthand. So if the question doesn't say that, then you're more than welcome to use shorthand. Let's do the shorthand method for potassium, which is number 19. What you do is you look for number 19 potassium, look to see what is the previous noble gas behind it, which would be argon. And then you use the brackets, not the parentheses, and you put argon in the brackets. And then you see that potassium is in the 4th energy level, in the S block, and it's 1A, which means it's got one valence electron. So that is the shorthand method to write the electron configuration for potassium. And if I were doing calcium, I just change that 1 to a 2, okay? And so on and so forth. So unless the question says not to use shorthand, I perfectly will accept the shorthand method. Just make sure that that noble gas is in the brackets and not the parentheses. That is the correct notation, the brackets. Any questions about the shorthand method? Okay. All right, so going back to the ions, remember we're making ions, and these ions are going to have a specific name. All positive ions have what their new name is called cations. The negatives have their own name, are called anions. And we'll have more on that in a second. All right, in this particular question, they're asking to write the electron configuration of potassium. Okay, we just did potassium, but you gotta make sure you read the question carefully, because you see here is potassium with the +1 charge. So they're asking for the electron configuration of the ion and not the element. The same is true for nitrogen. Nitrogen is in group 5. Nitrogen is a nonmetal. So nitrogen will gain 3 electrons, okay? Gaining 3 electrons, it has a net negative charge, net -3 charge. And then we got potassium here. They're giving you the +2, also asking you for the electron configuration for the ions. So be careful when you read the questions. Make sure you're not being asked to do the ions versus the atoms or the elements themselves. And that being the case, you see that both the N3 negative and the magnesium ion are all isoelectronic with neon. They have the same number of electrons, which by the way, when nonmetals become ions, we change the name. So nitrogen is the name of the element, okay? When it becomes an ion, we change the name to nitride, okay? In fact, all the nonmetals, when they become ions, their name changes. So oxygen is the name of the element, obviously. Okay. When it gains 2 electrons and becomes ionic, its name becomes oxide. Okay. Another one would be, say, fluorine. That is the name of the element, fluorine. And when it becomes ionic, by picking up 1 electron, its new name is now fluoride. That is what we brush our teeth with, is the fluoride. If you use fluorinated toothpaste, you're using fluoride and not fluorine. And so naming is very important, because you will be given like word problems, and they'll talk about questions that have the name nitride and not to be confused with nitrogen. Or they may say oxide and not to be confused with oxygen itself, the element, okay? Now, with respect to the metals, when they become ionic, the name doesn't change. So potassium, what we do, we'll say potassium element or potassium atom to be the neutral element. But once it becomes an ion, it's just called potassium ion. It's just the nonmetals that get their name changed, okay? So phosphorus, for example, will become phosphide. Okay, and then we have fluorine, fluoride. Fluorine becomes chloride. Iodine becomes iodide. Right, let me clear that. So here we're talking about the ionic charges. Okay, and depending on the group that they're in and whether it's a metal or non-metal, will tell you what is the ionic charge they would have. Group 1, as we know, has one valence electrons. All those elements have one valence electrons, so they will become negative charge, or excuse me, positive charge. Let me share another periodic table. This one right here. Okay, and so you'll see that group 1 in the far left, when they become ionic, those elements, the metals, hydrogen will also do, but right now I'm just talking about the metals, all will end up with a positive 1 charge. Group 2, all will end up with a positive 2 charge. Okay. Let me do one more thing here. The nonmetals, when they become ionic, I'm just going to start, not do all of them, just some of them. Okay. The nitrogen and the phosphorus, they're going to gain 3 electrons. They're in group 5. They end up with a negative 3 charge. Oh. Okay. So the nitrogen becomes nitride with a negative 3 charge. Phosphorus becomes phosphide with a negative 3 charge. Okay. Now, the ones in group 6, what do you think they're going to have? Negative 2 charge, because they need 2 electrons to get that octet. And so oxygen becomes oxide, sulfur becomes sulfide, selenium becomes selenide. Okay, a little bit of a tongue twister. And then group 7 all end up with a negative 1 charge, the ions. Okay. So fluorine is fluoride, chlorine is fluoride, bromine becomes bromide, and iodine becomes iodide. Okay. And so those are the ions. Now, I circle some other ones that always, more on those later on. And they, all the other ones, the B elements, their charge can vary. So we can't predict very well, with the exceptions of the ones that I circled there: aluminum, zinc, silver, and cadmium. Aluminum always has a +3 charge. Zinc always has a +2. Silver will always get a +1 charge, and CD, or cadmium, always has a +2. Okay, and so when we get to this, we'll have more to say about that. All the other ones, all the other metals can vary. And for example, there, copper can exist in 1 or 2 states of ionic state. It could end up as a +2 charge or a +1 charge. Iron, for example, is another example that can be a +2 or +3. So we can't predict with certainty what that charge is unless we know more about the reaction that they underwent. Here. All right, so this is basically what this is telling. This slide, group 1A, +1 charge, and so forth, okay? The other end, we have the nonmetals that, again, by gaining electrons, they're going to pick up an X number of electrons to have that octet. So nonmetals always gain electrons. You got to put that in long-term memory. And their name now, they're called anions, okay? For nonmetals. For metals, by losing electrons, they become cations. And here's the respective charge, like I just showed you in the periodic table, -1 to -3. Now the guys in group 4, and let me pull this up. They are on the wall, okay? Meaning on the fence, I should say, because they have the capability of losing. They got all of them got 4 valence electrons. And they have the capability of losing all 4 electrons or gaining 4 electrons, or any combination thereof. And so their charge can vary from a +1 all the way to a -4. Okay? So it depends on the reaction conditions and so forth. So we can't say definitely these guys are going to have this particular charge. All we can say is they're going to have a range of +1 to a -4 because they got 4 valence electrons. Once you go into group 5, they're all going to gain electrons. Anything less than group 4, they tend to lose electrons. Okay. All right. So, all right. Metals lose electrons; they become cations. Nonmetals gain electrons; they become anions. Okay. Now this part is important to know that, because when we're going to start putting compounds together, keep in mind we started with the elements. We talked about the elements. We talked about the electrons and how they occupy. We talked about why some of the metals want to lose electrons and why the nonmetals want to gain electrons, because we're going to start putting the cations and the anions together now to make compounds. And from the compounds, we're going to start putting compounds together to make chemical reactions. Okay. All right. So group 4, as I mentioned, can vary from a plus to a -4. And group 8, nothing's going to happen to them. Why? Because they're stable. They're the noble gases. They're stable because they already have 8 electrons. They have 8 electrons on valence shell, with the exception of helium, which its rule is a duet. Okay, there's no more room for more than 2 electrons. Okay, and going across the periodic table for the A elements, those are the prospective charges from a +1 on the far left to a 0 on the far right. Okay, well, here the question is asking you, what charge ion would they become? All right, well, to answer that, you're going to find them on the periodic table. So, like I said, the periodic table I will point to all the time. But once we know where it's at, that tells us how many electrons they have in the valence shell. And then once we find them on the periodic table, it tells us whether they are metals or nonmetals, which then tells us whether they're going to lose or gain electrons. And their position in the periodic table will tell us how many electrons they're going to lose or gain. Okay, lithium is in group 1, has 1 valence electron, and it's a metal. Being a metal, it's going to lose electrons, and hence the ion will have a +1 charge. Magnesium is a group 2A metal. Okay, again, it's going to lose 2 electrons because it has 2 valence electrons on the valence shell. Sulfur 1, it is a nonmetal. Okay, so it will gain electrons, and we got to find it in the periodic table, and it is in group 6, Roman numeral 6, which tells us it's going to gain 2 electrons because it has 6 valence electrons and needs 2 more to fulfill the octet. So it becomes a -2 charge. Now, whether you write it 2 minus or -2 makes no difference, as long as you got the minus in there. Which, by the way, when we talk about charges, you have to put the plus or the negative. Putting the 2 up there, it doesn't tell you whether it gained or it lost. Okay, so make sure you do add the plus symbol or the negative symbol. Bromine, nonmetal, okay, group 7A, has 7 valence electrons and needs 1 valence electron. So it becomes a Br negative, okay, superscript negative. Its name goes from bromine to bromide. Sulfur went from sulfur to sulfide, IDE. Nitrogen is in group 5. Again, also a nonmetal. Being a nonmetal, it will gain electrons. Being in group 5, it will gain 3 of them. So now it has a net charge of a -3. Also, its name changes from nitrogen to nitride. Okay. And then aluminum is in group 3, has 3 valence electrons. It's a metal. It's going to lose electrons. By losing electrons, specifically 3 of them, because it's in group 3, okay, and now has a +3 charge. The name doesn't change other than aluminum ion. The same for lithium, lithium ion, and magnesium ion. Only the nonmetals, we change the name. Now, you can combine and contrast. You have access right now to compounds. You start making compounds. Now, the thing to remember about making compounds and putting them together to write a formula is this particular, at this point, it's going to be this particular equation. The number of cations, okay, that is the number of positive charges plus the number of anions for right now equals 0. Oh, I don't know how to spell here. Okay, so I got to put enough positives and enough negatives together so that each positive and each negative cancel each other out. Okay, and so let's do a quick example up here. Let's take lithium, the lithium ion. Lithium ion has a +1 charge. Okay, and the bromide has a -1 charge. Therefore, when I put them together to write the formula, I can put them together as a 1-to-1. So that becomes lithium bromide. That is the formula for LiBr. Lithium bromide is the name. Eventually, we get to the point where, given the name, you work backwards to write the formula. Or, given the formula, go forward to give the name. So going back and forth, back and forth. Okay. Now, we can combine lithium, again, same example. We can combine it with sulfide. Bear in mind that I don't have subscript here, so that's the subscript. Okay, I can combine them, but here, remember this, I got to add enough cations plus enough anions to equal 0. So how many lithiums do I need to cancel out the -2 of sulfide? Yeah, exactly, Claire. You need 2. And this is where you now have control of the subscript. I don't have the subscript here, but you can write it out longhand if you want on your pencil. But that being the case, then it would be Li subscript 2S, okay, which would be lithium sulfide. That would be the name of that, okay? Now here you have access to all of them. You can combine the lithium with the sulfide, the bromide, and the nitride. So you got 3 compounds there. You can do the same with magnesium, magnesium sulfide, magnesium bromide, magnesium nitride, okay? Or you use the aluminum. So right now you probably, with all the metals that we have, you can probably put together a good couple hundred compounds at this point, and even come up with reasonable names for them, okay? Keeping in mind that the nonmetals change name to the IDE sulfates. Right. But there's a whole chapter on naming compounds and so forth, but this is an introduction to that. Isoelectronic, I just mentioned what isoelectronic means. It is having the same, iso meaning the same, electronic meaning trying to describe electrons, having the same number of electrons. Okay, and so the magnesium ion is isoelectronic with neon. They both contain 10 electrons. They're not the same. That's important. Nobody lost any protons. Okay, we just lost electrons. Phosphide, by gaining electrons, 3 of them specifically, because it's in group 5, it is now isoelectronic with argon. And so coming together, okay, it needs, by losing or gaining electrons, these elements now have the octet fulfilled with respect to its new valence shell. Okay. All right. So here you got a table, and they're asking you to write the electron configuration for both the calcium ion, the oxide ion, the chloride ion, and the aluminum ion. Okay. By doing that, notice that valence shell, the new valence shell is the octet has been fulfilled. For calcium ion, that is the new valence shell. It's a third energy period. The element, its valence shell was at 4s2. Those 2 electrons are lost. Now I got the new valence shell, the next one in. Okay. Let me ask you a question here. Based on what you see with respect to diameter, let's compare calcium right here, ion, with the calcium atom. Which one would you predict to be larger in size? The calcium ion or the calcium atom?
The atom.
Okay, I got 1 ion and 1 atom. Okay, but let me show you something else, and maybe this will help you. That's the electron configuration for the calcium ion. Now, if we were to, let me see how I can do this. Okay, I know exactly how to do this. Let's, let me do something here real quick. Okay, new share document. Okay, let's do the electron configuration for the calcium itself. Okay, so 1s, 2, 2s, 2, 2p, 6, and we're going across, we're going to calcium. Calcium has 20, so now we got to go to 3s, bear with me, 2s, 2, 3p, 6, and 4, finally, because calcium's in the 4th energy level, 4th period, 4s2. Okay. Now, does everyone agree that that is the electron configuration for the calcium element. Did I miss anything? Okay, the element is bigger. Okay, because what's going to happen now, if we take all this and we create calcium ion has okay, when it lost 2 electrons, remember this is the valence shell. That is the valence shell of the calcium atom. So the fourth energy level, fourth period, has 2 electrons in the outermost shell. When it lost 2 electrons, now the valence shell now is in the third energy level. That is the valence shell. And so the cation, the ion, became smaller in diameter. The fourth energy level is empty. It lost those 2 electrons. So the diameter of the ion, the metal ion, is much smaller, okay? Much smaller than the element itself. All right, let's do this. Let's take fluorine. Okay. Okay, so fluorine 1s. Fluorine B1s 2. Let's do this. It'll be quicker. What do we got? 5. Okay, would everyone agree that's the electron configuration for fluorine? Okay, now does fluorine want to gain or lose electrons? Exactly, it wants to gain. It's a non-metal, okay? And so before I proceed here, let me make something here. So the diameter of cation smaller than atom, talking with calcium. Okay, now when the fluorine picks up an electron, now it has a -1 charge. And now it picked up 1 electron, okay? And therefore, remember, electrons have a negative charge. So where it had 5 before, now it's got 6. There's more repulsion occurring now at the 2p orbital. And so the diameter of the ion for the anion is bigger, okay? Because by picking up the electron, so the diameter of anion is bigger than the atom, okay? Or an anion. So the anions become bigger when you compare them to the element that it came from, because it picked up an electron. The electrons repel each other. They take up more space. The cations, the diameter of the cation is smaller than the atom it came from, because by losing electrons, the next valence shell is the next level in. So therefore, its diameter is smaller, okay? All right, let's go back to This one here. Going back to isoelectronic, so the calcium ion is isoelectronic with argon, neon for the oxide and the aluminum, and argon for the calcium and the chloride. Okay, so the ions now have combined, have lost or gained electrons, so that their valence shell, new valence shell now is full. Now let's take a look at this last table. Here, they're giving you the mass number. Remember, the mass number is the symbol is upper left, superscript left. So they're telling you selenium 78 and selenium 78 -2. That's the ion. And you got aluminum 27 and aluminum cation of aluminum 27. Okay. So obviously we're dealing with selenium. We're not doing nothing with respect to the protons. We haven't changed anything. And so Sc will have 34 protons, or Sc selenium ion will have 34 protons. The same is true for aluminum atom and the aluminum ion. We have not done anything to change the number of protons, nor have we done anything to change the number of neutrons. Okay, so selenium 78, either as an element or an ion, still maintains 44 neutrons. Aluminum, also true, still maintains, in this case, 14 neutrons. The thing that differs is the number of electrons. Selenium went from 34 to 36, hence you got a -2 net charge. And aluminum went from 13 as an element, to 10 when it lost those 3 valence electrons, resulting in a net positively charged. Okay. That being said, we are done with chapter 5. Okay. And what I want to do is start with chapter 6, which is the very short chapter, very short, only 25. Okay, but let's take a quick short break. I'm going to do something real quick, and give me 5 minutes, and I'll be right back. Okay, guys, I'm back. All right. Any questions before we proceed? Comments, concerns? All right. Let's talk about the periodic table. Chapter 6. Very short chapter. Okay. Well, periodic tables fairly old. Actually, Dmitri Mendeleev back in 1869 proposed a periodic table. What's the amazing thing about this is that, this is a time period that really didn't have a lot of, scientific equipment and so forth. So he based this a lot on observation and the elements that they did know of and how they reacted, and put them in groups together and as far as their reactivity. Not really understanding why that was the case until now, where we talked about the orbits of the electrons and so forth. But one thing he did show, he proposed during his time that there were about 10 new elements, of which 8 of them were actually found later on. So the periodic table did open up a lot of scientific research to look for these elements that were yet to be discovered. So it wasn't until mostly later on, much later on, proposed a periodic table where he arranged them with increasing atomic number, okay? And then proposed what's called the periodic law. Elements in the same column have similar properties, and we understand that now, why that's the case. That's because they share the same number of electrons, of valence electrons, and therefore have very similar reactivity, okay? There are other elements out there. Why? Notice the bottom 2 rows. They tend to pull them out of the periodic table just so we can see the whole periodic table in a much easier viewing. But in reality, this group down here in the bottom, which have their own names, we'll get to those in a second. If we were to put them back in, the periodic table would look like this, okay? A little bit more difficult to really utilize. They're also proposing to change the numbering sequence on top. Notice the columns are numbered 1 through 18 and get rid of the Roman numerals. Now, that's still up in the air. I think the Roman numerals do offer a lot more information because they're telling you how many valence electrons exist in that particular column. Okay. But not only do they give you how many electrons, valence electrons they have, that is the Roman numerals, but they also, and I'll show you how you can tell it, it would tell you how many bonds they can actually make, besides how many electrons they need to become isoelectronic or the noble gas. But that naming sequence is still up in the air. They haven't decided what the official periodic table. There are a whole bunch of other periodic tables. Some have proposed a circular periodic table. There are some pros and cons to this. Give you an idea of one here, the spiral periodic table. There's another one that's not bad, kind of looks complicated, but it's like the spiral periodic table. But this one here actually predicts a bunch of more elements out there. And you'll see up there in the upper top where you got the what they call superactinides. Those haven't been found yet or been made. Actually, the elements starting from 92 forward are actually man-made, and a lot of them are very radioactive. Anyway, Niels Bohr, whom we talked about in the previous chapter, introduced the energy levels, okay? And this is where I use the example of the S block, the D block, the P block, and the F block elements, okay? Which represent the orbits or the sublevels of the sublevels of the orbits. Notice the numbering, 2s, 3s, and so on and so forth, and you get into the P block and the D block, so forth. So the periodic table is very useful as far as being able to quickly write out the electron configuration for um, any of the elements without having to memorize the sequence that you saw on that table that I gave way back when. Anyway, the horizontal row, it has its own name, we call them the period, which is also the energy level, but you'll see here the term a lot with the period. And the vertical columns are called the group. You also will hear the term family, meaning the family of whatever group it's in. Okay. And that's because elements in the same group exhibit similar properties due to the fact they have very similar valence electrons. Okay. Now the ones that have the Roman numeral A, they have their own little name. Those are called the main group elements. That's all of the A group, Roman numeral 1A to 8A. The F block and the D block or the B elements, they have their own little name too. Those are called transition metals. Okay, transition metals. So we got the main group elements, and the transition metals are starting with the D block. Okay, so this represents the period, or the energy level, or the shells is another term that is utilized. And then we got group or family. Now, some of these groups have their own little special name, which I've highlighted here. The group 1A, with the exception of hydrogen, because it's not a metal, okay, are called the alkali metals. And the group 2A are the alkaline earth metals. Now the group 7, where you got fluorine, bromine, chlorine, those have a special name too. Those are called halogens. You may be familiar with halogens. Some of you are using bulbs in your vehicle or halogen lamps, okay, very bright light. And then the last group, the 8A, those are noble gases. Okay, the noble gases, again, called noble gases because they're very unreactive, again, because their octet is fulfilled. Okay, so here we have the group B, the transition metals. Okay, we can't predict very well their charge, and as I mentioned in the previous slide of my charges, that these metals can have a variety of different charges. Copper, like for example, can have a +1 or have a +2, and we can't really predict it. We can calculate it, and I'll demonstrate how that can be done, because in every compound that you will see, though you may not know the charge of one of those elements, one of those ions, you'll always know the charge of the other one. Okay, so that will allow you to predict what the charge is of the unknown. Now, those two series, the two rows that are pulled out, they have their own name. They're called inner transition metals. Okay, and within that general name of inner transition metals, they have their own series name. So the very first row are called the lanthanide series. Okay, otherwise they're also called the rare earth metals. And then the row below that is called the actinide series. All of them are radioactive. You'll see the atomic number, which atomic weight, excuse me, is in parentheses. Those elements you find in parentheses are radioactive and difficult to actually calculate their specific atomic weight. So you'll see them in whole numbers there as far as your atomic weight is concerned. Elements that are greater than 93, all of them are man-made. They're put in particle accelerators and they actually crash these elements together to create new ones. Okay. With that being said, questions might come arise at stake. And the alkali metal in the third period, Okay, third period. So we go through the third period, and then remember what are called alkaline metals, and we find that that is sodium. Okay, a halogen, which is in group 7 in the second period, and that would be fluorine. Notice I said fluorine and not the term fluoride. And then the noble gas in the fourth period would have to be krypton, Ar. Okay, because halogens are in the far right. Now, refresh your memory with respect to metals, nonmetals, and metalloids. Okay, this is important to be able to recognize what are the metals and what are the nonmetals. Why? Because in the next chapter, we're going to be talking about chemical bonding. And in chemical bonding, there's only two types of actual bonds. One is called an ionic bond, and the other one is called a covalent bond. Okay. An example would be sodium chloride. Sodium chloride is an ionic bond because what is defined as an ionic bond is a combination of a metal and a nonmetal. So hence sodium chloride, you got sodium, which is a metal, and chloride, which is a nonmetal, is therefore an ionic compound. A covalent compound are those chemicals that are made up of nonmetals. Classic example will be water, H2O. We have a hydrogen and oxygen, both of them nonmetals. That is a covalent compound. And being able to recognize the difference between the two will assist us later on down the road when we start to look at properties and a variety of different things. Okay. All right. So now the atomic size. That's the distance from the radius. It's the distance from the center to the outermost electron. And let's, based on what you can conclude right now, okay, just based on the information that you have, just take a look at this. What would you predict to be larger in size with respect to radius if I were to look at fluorine versus bromine? Which of these two elements would you predict to be larger in size, would have the larger radius? What we got here? Exactly, Claire, bromine. Because bromine is in the fourth energy level. It's got more energy shells, okay? So it's much bigger ball, so to speak. It's bigger, all right? And that makes sense there, all right? So, let me clear this up. What if I were to compare the diameter of, say, carbon to fluorine? Would you predict which one of these two would be larger? Exactly, the fluorine would be not larger. You notice what I said? Fluorine would be not larger in diameter. The carbon would be larger. Okay, let's think about this for a second. Let's look at carbon. Carbon has 6 protons, 6 electrons. Fluorine has 9 protons, 9 electrons. Okay, and so there are more positive and negative interactions. Basically, we got more magnets. There's that force that's coming that attracts the proton and the electrons. And so with fluorine having more protons, the force of pulling the electrons in is much greater than carbon. Therefore, the result is that the radius of the fluorine gets smaller. okay? And so to rehash, going down the periodic table, the radius gets bigger. It makes sense. We just get into larger energy. But as we go from left to right, the radius gets smaller because we increase the number of protons and we're increasing the number of electrons, resulting in a stronger force of the protons and electrons, that stronger interaction, pulling them in much tighter, resulting in a smaller radius as you go from left to right of the periodic table. Okay? And so it increases down the group, but we go from left to right, they get smaller in diameter. So we can use the snowman to kind of help you out. The snowman represents the head of the radius, the circles. And so going down the periodic table, you can see the bottom of the snowman gets bigger, okay? So take the snowman and tilt it to 90 degrees to the right, and therefore the radius, as we go from left to right, they get smaller. The train gets smaller because we're increasing the protein and electron, proton and electron interaction, and those electrons being pulled in closer, okay? So already you picked up on some trends. We talked about the cation and the anion with respect to radius and which one would be bigger, okay? And now looking at the periodic table, we can predict which element would be bigger in size or smaller in size, depending on how you look at it, depending on its position on the periodic table. Okay? This particular table kind of gives you the trend. Now, what happens when you get down into inner transition metals, and it's that bottom two rows, the radius, the elements there are so big, there's really not much difference occurring. So mostly the main elements that you'll see that general trend as you go down the periodic table, they get bigger. And the general trend, and I repeat, the general trend from going left to right, the elements get smaller. So these spheres represent the relative size of the elements in the periodic table. Okay. So you may be asked a question, well, which is larger? And they're giving you three elements here, oxygen, selenium, and beryllium, and then they want you to ask you why. Well, to answer the question, you need the periodic table, okay? And I got an image of the periodic table there, and I marked the elements of question. I circled them. And I can see that they're all in the same group. They're all in group 6. So that means going down the periodic table, they get bigger because beryllium is simply a bigger element. It has a higher energy level, a larger radius. The question B, asking you to compare the radius, which one's larger, magnesium, silicon, or sulfur. And so again, I have an image there. I have to find them on the periodic table and then mark them. So I got magnesium on the far left, and we got sulfur here on the right. And obviously, the trend from going left to right is that it gets smaller, but other than just regurgitating the trend, go on to explain why that is the case. And that's simply because we got more protons and we're pulling the electrons in closer as we go from left to right on the periodic table. Okay. Now, on the course website, there are some YouTube videos with Dr. Kim concerning the atomic size. You know, feel free to obviously go up there and view it. You know, the more information, you can't go wrong. Okay. All right. Now, there's a property here we call ionization energy. In fact, there's two properties we're going to talk about, and it's important that we don't get the two confused. Okay. This one, called ionization energy, is the amount of energy required to remove an electron from a neutral atom. Down the road here, a couple slides, we're going to have what's called electronegativity. That's a different property. But right now, let's talk about ionization energy. And the way that's demonstrated is by that equation, where you have sodium given an X amount of energy, and the drive here is to remove an electron, okay? And so we see that what we find is that ionization energy increases up a group, okay? Now, you might think, well, why is the case? Well, if you look at the periodic table, okay, let's go back to the periodic table for a second. And let's just pick, within a group, let's just pick a couple of elements. I'm going to circle them. And if we look at lithium compared to potassium, okay? All right. So what they both have in common is obviously they're metals, okay? But they also have in common one valent electron. What they differ is that lithium only has 3 total and potassium has 19 total. But they share the fact that they got 1 of their total in the outermost shell. Now, potassium's electron is in the 4th energy level. And so it's further away than from the nucleus than the valence electron for lithium, okay? So it stands to reason that that electron for potassium there's less interaction between the nucleus because it's further away. Yeah, if I'm interacting with my electron and I represent the nucleus, and let's say my electron is a mile away, okay, I have an X amount of interaction going on. But if I have an electron that's 5 miles away, yeah, there's an interaction occurring, but not as strong as if the interaction was, say, 1 mile away, okay? And so, with that being the case, the ionization energy, the amount of energy necessary to pull that 1 electron away, will be much less within the group if the electron is further away from the nucleus, okay? That stands to reason. Now, when we go from left to right on the periodic table, okay, well, a couple of things. Just like the radius, as we go from left to right, there are more protons, and therefore those electrons are being held on tighter with those elements that have more protons as we go across the periodic table. Okay, and so let's do an example. If we look at and compare, let's say again, lithium with fluorine. Okay. Well, the ionization energy for fluorine will be much greater for 2 reasons. Okay. One, the same reason the radius is much smaller, because fluorine has more protons to hold on and to pull those electrons. So it's going to take a lot of energy to yank off 1 electron. That's one reason. Second reason is lithium is a metal, and metals, by the nature of the beast, want to give off electrons. So across the periodic table, if I'm comparing the metal and the non-metal automatically is going to have a higher ionization energy, okay? But if I'm comparing 2 non-metals, let's say nitrogen and fluorine, again, fluorine wins the bet here because nitrogen has less protons, and therefore the strength necessary to hold on to those electrons is much less than fluorine, because fluorine has more protons. Okay, just like the reasoning with respect to the radius. All right. All right. So if we look at the table, a graph of the of this ionization energy, you can see that the trend, how the trend works. So let's start with hydrogen. Let me change the color here. Okay, if we start a hydrogen right here in the far left, it has ionization energy, I don't know, somewhere around 14, 13 and a half energy units. And we shoot across the helium, across the periodic table, that one's almost 25 energy units, or electron volts, quite high. Then as we wrap around the periodic table, we're back to lithium, which starts here, and we go across the periodic table to neon, and the energy increases when we get to neon. Neon's all the noble gases because of the octet again, and they hold on to their electrons much tighter than the rest of the elements within the same period. And then we shoot back to sodium, start over here in the far left, shoots across to argon, okay? And the general trend, again, it starts to decrease as we get bigger and bigger in size. You notice our arrow, the slope of our arrow gets to get much, much less as we go in bigger elements, because the elements are getting bigger and now the effect is not as strong or not as drastic with respect to the smaller elements. But the general trend is still there. Is as we go left to right, the ionization energy increases. Okay. And so here they're asking you a question. Which has larger IE and why? Well, they're asking us to compare chlorine, aluminum, and magnesium. Okay. Now, you may not even need to look at the periodic table here, right? Because first thing to look at is to see that one of these is a non-metal, okay? And the other two are metals. And therefore, just with that observation, chlorine is going to require a higher ionization energy because the nonmetals are less likely to give up electrons. Can it give up electrons? Yes, but it takes more energy, a lot more energy, as compared to aluminum and magnesium that are metals and they readily give up their electrons. Now, if I were to compare magnesium and aluminum, aluminum would require more energy, obviously, because it has more protons and they will hold on to their electrons a little bit tighter than magnesium would. Right. So now if we compare a different group, lithium, rubidium, and potassium, well, guess what? They're within the same group, okay? And so RB is much bigger. And what they share, all three of them shares one valence electron. But again, the valence electron for RB is much further away than it is for lithium. And therefore, lithium, being the smaller of the elements, just holds on to its electrons much stronger than the bigger elements. All right. Again, we have a video on ionization energy, so you may want to take a look at it. All right. Which brings us to electronegativity. Now, this concept here, this is going to pop up, especially in the next chapter, because this plays a big role on the properties of chemicals and why certain things are what we call polar and why certain compounds are what we call nonpolar, which affects solubility in water, which has an effect on boiling point, on surface tension, and viscosity, and so forth. So electronegativity is something you need to grab a hold of. Okay, now to determine the trend is from left to right, it goes up, from bottom to top, the electronegativity goes up. What we have here is fluorine. Fluorine is about right, let's just say, I don't know, better yet, let me bring the periodic table. Fluorine is our benchmark. Fluorine is our reference point because fluorine is the most electronegative element on the periodic table. and everything is relative to fluorine with respect to electronegativity. What electronegativity is a measure of the attraction of electrons in a bonded compound. So the ionization energy dealt with just the atom by itself, the element. Here, we're actually talking about a bond, a chemical bond of some sort. And normally that chemical bond, we share electrons, okay? And we have either equal sharing or unequal sharing. If there's a difference in electronegativity between two atoms that are bonded, okay, there's going to be unequal sharing. And that in itself has an effect on a lot of things. And so the trend, as stated, is left to right goes up, bottom up goes up. And so if I were to compare the electronegativity of, let's say, I want to compare the electronegativity of carbon, wrong one, wrong image here, of carbon versus oxygen. Which one is more electronegative, carbon or oxygen? Anybody want to take a guess? Don't have to guess. What you do is you find fluorine, you know where fluorine is. Now look at the position of the two elements in question and determine which one is closer to fluorine. Obviously here you can see that oxygen is much closer than carbon is. Therefore, oxygen is a lot more electronegative than carbon, okay? That means if we were to have a bond between carbon and oxygen, oxygen will have a tendency to pull the electrons in that bond onto itself much stronger than carbon would. Okay.
So it doesn't matter which direction you go away from F, it's always less?
Let's go back to it. When you mean by direction?
So like left or right, it's always lesser than fluorine?
No, fluorine is the most electronegative.
Mm-hmm.
Okay, and so in that example of carbon and oxygen, with oxygen being closer to fluorine, that means when I just compare carbon and oxygen would be more electronegative than carbon.
Okay.
Okay, and if I were to compare, let's do one more comparison. If I were to compare, let's say oxygen to chlorine, okay, who would be more electronegative, oxygen or chlorine in this scenario? Well, the oxygen would be more electronegative because oxygen is in the same energy level as fluorine, whereas chlorine is one level down, okay? And so we use this fluorine as your benchmark because down the road when we do a for example, if we have a bond between carbon, and I'm going to denote that by this hyphen. This hyphen represents a bond between carbon and nitrogen. And that hyphen represents 2 electrons in this bond, okay? Now, when I want to know which one's more electronegative, carbon or oxygen, I compare carbon. Yeah, let me change the color here so we can distinguish. I'm comparing carbon and nitrogen. Okay, now, who is more electronegative here, carbon or nitrogen?
Nitrogen?
Nitrogen, exactly, because nitrogen is a lot closer to fluorine. What does that tell you then? That tells you that that bond, let's go back to the bond, between carbon and nitrogen, that the electrons are being pulled toward nitrogen, okay? Now, if I were to look at a bond between nitrogen, again, that hyphen represents a bond, and I look at a diatomic compound, okay, where I have two nitrogens. Well, there's no comparison there. The electronegativity of two nitrogens is the same because they're the same element. So therefore, there wouldn't be any pull whatsoever. So that hyphen, which represents a bond, there will be an equal sharing of those two electrons in that hyphen. Whereas carbon and nitrogen, it would be an unequal sharing in those two electrons represented by that hyphen, which represents a chemical bond, okay? Which means that the nitrogen would be what we call more nonpolar compared to carbon nitrogen, which would be more polar. Now, what we mean, I'm sure you all heard like dissolves like. We all know that it's difficult using just water to wash off oil, right? Water and oil do not mix. Don't believe me? Take a bottle of Italian dressing. Okay, you got two layers. You got the oil layer and you got the water or the aqueous layer. They don't mix, okay? Because oil is what we call nonpolar, and water is what we call polar. And so by looking at the bond here between carbon and nitrogen and nitrogen, figuring out that nitrogen is nonpolar, we can make the prediction that with respect to solubility in water, the carbon-nitrogen bond will be more soluble in water than the nitrogen-nitrogen bond, and vice versa. The carbon-nitrogen bond will be less soluble in the oil-based or nonpolar solvent. Okay, and it's all related to the electronegativity of the two elements that are bonded together. We're going to get deep into this down the road when we talk about intermolecular forces. And these are forces of the molecules interacting with each other. Things like, we all know if you take a cup of honey and a cup of water and you empty them, who's going to win the race?
Water.
Of course, the water, right? Because the honey is very thick. And the reason it's very thick, it has to do with the interaction of the honey molecules with each other, which is related to how the bonds are put together, whether we got a polar bond or a non-polar bond. Okay, we use this product quite a bit. That's basically how detergents and soap work. They have polar properties and non-polar properties. Soaps are made up of a very non-polar group that will dissolve the oils and greases that normally don't get dissolved in water. But the detergents also have a part to it that is very polar, so that when the non-polar end dissolves the oils and greases, then the polar end gets washed away with the water, and therefore you cleanse your clothes or your detergent or your shampoo. And it all has to do with this crazy electrons again. All right. So that being said, electronegativity. So we're introducing the topic here. So, but don't forget it because it's going to come again over and over again in subsequent chapters. Okay. We know that noble gases don't have any electronegativity values because they just don't form bonds. Okay, there's nothing for them to do. They are inert. With that being said, that brings us to tell you this is a short chapter. Chapter 6 is done. So that should get you ready for the exam next week. And if you have any questions, by all means, feel free to stop by here on Mondays. I'm here on Mondays, 1 to 2 for office hours. And you're also more than welcome if you have the time to come in. I got a 1 o'clock session and a 4:15 session on Tuesday and Thursday. Okay. Feel free to